just to show hands, how many of you are familiar with an idea of open sets or closed sets? Yes, no? Fine. So, the aim of this talk is to solve one or two problems in discrete maths and graph theory using theorems in topology, as in geometry. So first we'll establish some notation and then I'm assuming everyone knows this. This is just n times, and this is given by the n sphere, which is throughout this talk, if you want to be visualizing things, it's best to do it when n equal to 2 for S2 and S2 lives inside R3. So, Sn, yeah, it's great. Does that not look like S?
That does not look like it. But it's fine, I guess.
So this is what we'll be working with. In any case, you want to feel an idea of why a theorem is motivated, you just look at this example. The main theorem in both the problems we're going to be using is called the Borsuk-Ulam theorem. Which states if you have a continuous map from the n sphere, which sits inside n plus 1 dimensional space, into Rn, so that is you're killing one dimension, is continuous, then this symbol means there exists some element in the domain. So there exists some x in Sn, that is the n sphere, such that f of x is equal to f of minus x. So this is already a very strong statement. That is, you take any continuous map that does not tear the hollow sphere, and you're trying to put values on each point, just two values on each point. And it's saying that there are two antipodal points that are getting the same value. A consequence of this you may have heard is, at any given point in time, there are two opposite points on the earth which have the same temperature and pressure. Because temperature is a continuous function, pressure is a continuous function. So you can just apply the Borsuk-Ulam theory, treating the surface of the earth as a sphere. Okay. So we want to make the jump from this continuous topology theorem to discrete math. For that, we need to establish a technical result first, which I'll do pretty shortly. It's called the, I don't know how to spell it. It's called the Lusternik-Schneiderman theorem, which I'll just abbreviate by LS. So it states that, okay, if that is beyond the content of my talk, but we can discuss it later. So if you have A1 through AN plus 1 closed sets, so what does it mean for sets to be closed? Oh, AI subset of Sn. So this lives inside Euclidean space. Which in Euclidean space you have a notion of distance. You take an n tuple, you take another n tuple, you take differences component wise, you square them, you take a square root. That's just a Pythagorean formula for distance. You can just restrict that to the sphere in n space. So you get a notion of distance even in n space. So a closed set is anything such that so what does this mean? This refers to the minimum distance from a point to a set. So if I'm given the open interval 0, 1 and I ask you the distance of 0 from this set, well, it feels like it should be 0 because you can get arbitrarily close to the element 0. But 0 does not belong in this set because it's an open interval. So we say something is closed if you can get arbitrarily close to it, and if you can do that, then that element is in fact in your set. So that it means that's what it means to be closed. So if you have a n plus 1 closed sets such that their union is all of Sn, then so what it means is that if you take n plus 1 closed sets, you can at least that cover all of Sn. You can at least find one of them so that if you take its negative reflection on the sphere, they will always intersect. In other words, there is some element x such that x and minus x are both in AI. So,
can you repeat the theorem? I didn't understand.
Okay. So, did you get the meaning of closed? Yeah, it's irrelevant, but it's fine. It's closed. So, if you have n plus 1 closed sets covering Sn, then there is at least one of them such that that set contains a pair of opposite points.
Okay.
That's fine? Yeah. That's what it means. There is an I such that AI intersection, the minus of AI is not empty. Okay. So this can be generalized to say that A1 through An plus 1 need not be closed. They can be closed or open. Open just means it's the complement of a closed set. That's all you need to know. It's just complement of a closed set. And so you can generalize it to AI being either open or closed and n plus 1. Then this will still hold. The same result will still hold. We will prove that if there is time. Otherwise, we can just believe it for now. Okay. So the first problem that we'll be solving comes from a conjecture of Martin Messer. It starts as follows. Consider the set so this set I'm just going to abbreviate like this, and so you consider all k-side subsets of a set whose size itself is n. Now I'm going to create a graph whose vertices are elements of Fk. So we'll call this kg n comma k, which stands for Messer graph on n comma k, but it's fine. So when denoting a graph, we say vertices and then we specify the collection of edges. The vertices are just this. And the edges, we relate to k-size subsets if and only if their intersection is empty. Fine? We are going to do some examples, it will be clear. Okay, so let's find kg 4, 2. So it has we are starting out with a 4-element set and we are picking out 2-element subsets. When are two 2-element subsets disjoint when it's coming from a 4-element set? That is, it's precisely the complement. Yeah. So any and this is if and only if, because if you take any other 2-element set, if it's not its complement, it's going to intersect somewhere. So kg 4, 2 just looks like, well, there are 6 of them, so you just get a matching. This is what it will look like. So this is a pretty trivial example. Now kg 5,2 is a little more complicated, and I'll just draw it out. So this is called the Peterson graph. It is also a nice property that every edge shares, every vertex shares an edge with exactly 3 other vertices. You can see this because if you take a 2-element subset, how many other 2-element subsets are disjoint with it? So if you take 1, 2, the other 2-element subset its disjoint from must come from 3, 4 or 5. How many 2-element subsets can you form from 3, 4 or 5? It's a 3-element set, so 3 choose 2, 3. So therefore, any vertex shares an edge with 3 other ones, 1, 2, 3. Okay, so what Nesser was after was something called the colorability of a graph. What does this mean? Like, okay, you want to color the vertices of this graph so that no 2 adjacent ones, we say 2 vertices are adjacent if there's an edge between them, so that no 2 adjacent ones get the same color. So, how many colors does it require to color this one? 3? 3?
So 2.
Ah, yeah, just 2. Yes. So you can just give this green and. So of course, if you can color it with 2, you can color it with 3. That's not a big deal. But the question is, what is the minimum number of colors you need to color a graph? The vertices of a graph. So that number is denoted by chi of g. Okay, so what do you think the colorability of kg 5,2 is? The chromatic. This is called the chromatic number. Chromatic for color, whatever. This is the minimum number of colors. So you definitely need 3. Can you do it in 3? Yeah, you can do it. Why can't you do it in 2 would be the question. To claim that this is the minimum, you need to show 2 things. One, you cannot do it in anything lesser, and 2, you can do it in 3 colors. So, if you had only 2 colors,
you can choose any vertex and it's like this.
You choose any vertex, you give it some color 1. You have to give this 2, you have to give this, you have to give this. You have to give this 2, you have to give this 2, and you have to give this 2.
Yeah.
And so you just chase and find out that you get a contradiction. And so this is fine.
What's the construction for 3?
Sorry, it's a construction for 3.
You can have 1 at the top.
Okay.
2 are the left and right ones, the outer ones. And 3 are the bottom 2 ones. Then you can have 3 there.
3 here.
Yeah. 1 at the left and right one, the upper one. And 2 is below.
Thank you.
This works.
Yeah. Thank you. Okay. So, Nesser conjectured that phi of kg n comma k is just equal to n minus 2k plus 2. He did this by lots of experiment. Well, first we need to ensure that this is a non-negative number, a positive number. That is, if y is n greater than or equal to 2k minus 2. Well, if n were less than 2k, then what do you mean by 2 k-size subsets being disjoint when the vertex set itself is of at most size k? There is no such partition. So we can just consider n to be bigger than or equal to 2k. That's fine. So what we are going to prove is this statement. Yeah? Is everyone fine with this? This is the goal of this problem. I'm going to erase this. Is everyone comfortable with the two results here? Which one? This one?
The LS?
Yeah, LS.
The only conditions are that the sets are closed and the union is SS.
Yeah. And there are n plus 1 of them. That's important.
I mean, is there any condition like they shouldn't have any points in common?
Oh no, they can have points in common. That's not an issue.
I mean, can't
They will have points in
They will have points in common because it's something called connected.
Like,
It's a very strong theorem.
Yeah, how? What's the?
The proof idea for the closed set is pretty simple. The idea is, like you want to construct a function Sn to Rn, right? To such that you get antipodal points. So the function you construct is f of x. X is a n, like it has n plus 1 coordinates. So you take distance. You need an n tuple, so you take distance of.
I know the proof of closed set with equivalence.
Sorry,
I'm asking the proof of LS,
yeah, I'm giving the proof of this.
not for the closed set.
You want?
No,
or
I think
it
it's
is-
not equal.
Sorry.
No, nothing. I got confused.
The other way is also true, but we not. Okay. If you want, we can discuss the proof later. Do you want me to give the proof? It's pretty simple. Yeah, sure. So the function you construct is you take a vector as in an n plus 1 tuple in Sn. You consider this tuple, distance of x from a1 up to distance of x from an. Yeah, measuring distance is a continuous function. That is intuitive. I mean, you can prove it, but that's intuitive. So this is a continuous function from Sn to an n tuple. All of these are real numbers. So Sn to Rn. So there is f of x. There is an x such that f of x is equal to f of minus x. Case 1, this is 0. I mean, it is 0 in some coordinate. If it is 0 in some coordinate, then distance of x comma ai for some I is equal to distance of minus x comma ai is equal to 0. But by definition of closed, that must mean x and minus x belong to the same ai. Now, if none of them are 0, then x does not belong to any of the ai, but I consider only up to n. But the union is all of Sn. So x must belong to Sn, the n plus 1. And the same holds for minus x because f of x is equal to f of minus x. So minus x also belongs in n plus 1. So that this I is given by n plus 1. That would be the proof this way. We can discuss it in detail. I hand-waved a little bit, but that's fine. Okay. This is the theorem we will be using to prove this. Okay. So if I'm going to claim this result, I first show that there is a coloring of kg n comma k in n minus 2k plus 2, which is the first thing I will do. So what is a coloring? I am just assigning each vertex a color. Well, I'll probably run out of colors for n. So I'm just going to assign them numbers instead. So I'm going to construct a coloring function called from the vertex set fk to n minus 2k plus 2. I'm going to assign it 1 through n minus 2k plus 2 colors. So the color of a subset A, a case size subset A, I'm going to give it by minimum of this. I'm just pulling out of thin air. Don't ask me. So we first need to make sure that this is a valid coloring. That is, two disjoint ones do not get the same color. So suppose coloring of A is equal to coloring of B. Here A and B are k-size subsets. So if the coloring, it's being assigned as a minimum of the minimum element or this number. If both of them come from this particular argument, that just means A and B have the same minimum element. But that is literally telling you that they have an intersection. So that's one case. The other case is if min A, min B, yeah. So if this is not being chosen, then it must be that the minimum of both of these is bigger than n minus 2k plus 2, because I'm choosing the minimum for their color. That's fine. So what does this mean? A, comma B are subsets of, they have to start with this, n minus 2k plus 2 onto n. Yeah. This is a, how much is this? 2k minus 1. Yeah. So if A and B are both subsets of 2k minus 1 element set, they cannot be disjoint. Because if A and B are disjoint, then A union B would create a 2k size subset. So this case is also covered. So this becomes a valid coloring of KG and comma K. Any questions? Want me to repeat that argument?
Can you repeat the first?
The first case.
Yeah.
So if this does not happen, then both min A, min B is less than n minus 2k plus 2. But then by this function, the coloring of A and coloring of B is equal to min A and min B. But this is the hypothesis. So min A and min B are equal.
How are you assuming that color of this?
This is the, like, we want to verify that this is a valid coloring. How do you do that? You assume that two of them have the same color and show that they don't share an edge.
Yeah.
What does it mean to not share an edge in KG n comma K? They are disjoint. So I'm assuming this hypothesis, proving A intersection B is not empty. This is what I'm trying to prove. So if this happens, fine. Are you good with this argument?
Yeah.
If this happens, I mean, this is just the opposite of this, then you just have that minimum of A is the coloring of A,
Yeah.
because here, minimum of B is the coloring of B. By equality, minimum of A is equal to minimum of B. That just gives you an element of the intersection.
Okay. Yeah.
So this is not, that's fine.
Either the coloring is not valid now.
Where did I mess up?
No, I messed up, but both the two horizontal lines are the same. You can swap the 1 and 3 on the left. That will make it up.
1 and 3 on the left.
Yeah, like the bottom left 3 and the left point of the star. Okay, that's now
Yeah, I mean, the conjecture will give you 3, so it's it will be colorable in 3. Okay, so suppose so we got a coloring with n minus 2k plus 2 colors. If you want to show that that is the minimum, we just show that this minus 1 does not give you a coloring. So call this D. Okay, here comes the geometry bit. So to go into geometry, I'm going to realize these n points as points in some Euclidean space. Consider SD sitting inside. So I'm asking you to choose n points on the D sphere. I mean, this is a lot of words, we'll unpack this. Choose n points on the D sphere such that no plane passing through the origin. So a plane in R3 is just a sheet of paper that passes through the origin. Contains D plus 1 points. First, it might not seem that this is even doable, but okay, I might show you how to do this later. So, but for the D equal to 1 case, what does this mean? You have a circle and you want to choose n points so that no two of them lie on a plane passing through the origin. What does it mean to be a plane in R2? A line. So I want to choose n points so that no two of them lie on a line passing through the origin. If I choose 1 point, there's only one line that passes through the origin and that point. It's just this. So I'm pretty sure I can choose n of them so that they don't lie on, no two of them lie on the same line. The idea is you just generalize this to d dimensions. So there can be this point, this point, this point, this point. You can just fill it in very close by, and no line will intersect two of them. Okay. So define this particular set AI. So I'm going to use the LU theorem that I stated here. I need to first construct n d plus 1 open or closed sets, either all open or all closed. You can mix them up, but we will stick to the simpler case of the all open or all closed. So define AI as follows. A point x in Sn is in AI So note that what I'm doing is by choosing these endpoints, I'm identifying this set with these endpoints called as X. Yeah, so the k-size subsets can be realized as subsets of X also. And whatever coloring I took here, I'm just coloring points on the sphere ST. That's fine. I use the same. So, okay, again, a lot of words to unpack here. What is going on? So, what does it mean for the hemisphere of X? What does it mean to be the hemisphere of X? So, again, we go back to the three-dimensional case. So the point here, what does it mean to be a hemisphere containing this point? Well, a hemisphere is just, you take a plane and cut the sphere in half, and it should contain the point. To make it even in a say, you want to take this. This is the most natural dissection you can take for a hemisphere containing this point. That's true? Yeah. So for a point somewhere here, well, it is true, this hemisphere does contain this point. But I meant of X, so it must be sort of unique to this X. Instead, just rotate the sphere to the top, use the same plane and rotate back. It's just a like, okay, for this point, I should use a different job. It would be this. And this hemisphere. So these endpoints X are on this sphere. This condition is that there is a k-size subset, that is a k-size subset of X, sitting inside the hemisphere so that its color is this I. That is what DI is. How many such DI is there? Well, I told you that I'm trying to color it with these many colors. So, D many DIs. Should I change the name again? Give me a different letter. So you have M1, MD. Now I want D plus 1 sets. Yeah.
You mean X and S and S and
Yeah, I changed it. Then it should have been DI, now MI. I'm defining the elements of MI. Sorry?
Could you repeat?
Yeah. So I'm saying that this particular point is in MI if consider this hemisphere, the open one not containing whatever the plane is intersecting, contains some k-size subset of X that is colored by the ith color.
Open hemisphere.
Open hemisphere, yeah. So when I mean by hemisphere, I don't mean the boundary of the hemisphere is included. So when I mean in a circle the hemisphere, so I have to cut it like this. This is a hemisphere and I'm not including these 2 points. Yep. Okay. So I got M1 through MD. The point is that these sets are open. Why are they open? Because I'm taking some sort of open hemisphere, that is I'm not including the boundary. So if I shift this point by very little, then whatever this subset was still remains in the shifted points hemisphere. Because these points never lie on this boundary. So you can shift it by very little so that this set still lies in the hemisphere of X dash, when X and X dash are close by. So M1 through MD are open and all of these are subsets of Sn. So to use the LU theorem that I stated, I need it to be a cover. Well, right now it's clearly not a cover. I have no hope that it's a cover. So how do you just give me a cover? Yeah, I just took whatever is not there and put it into one another set. So now their union must definitely be ST.
Can you repeat the part?
So I want to extend this so that their union will be the sphere. I don't know if this is the union of this is a sphere. So how do I just give me one more set so that the union just becomes a sphere? I just take points that are not in all of them. So it's just SD minus the union. So the point I told you that complements of open sets are closed and complements of closed sets are open. This is an open set. This is fine. This is some abstract topology. You can ignore it. Okay. So I have a mixture now. Some open, some closed, and I don't know what to do. Can I erase this? Did everyone get KG and Tofu? You let it be. Sure.
That I corrected the
It's fine, someone can figure it out. Like the conjecture will tell you that this is 3 color. So now what the LS theorem would give if these satisfied the hypothesis is that there exists I such that x comma minus x, but there exists x also belong to Mi. Right, that was the theorem that stated the result of the theorem. We can't directly apply it because I didn't particularly make sure the hypotheses were correct. So if this did happen, what would it mean? Case 1 is that I is less than or equal to D. So I'll draw this here again. Okay, this is the hemisphere of X, call this HX. this is the hemisphere of h of minus x, this side. Yeah. So x comma minus x both live in Mi. That must mean there is a k size subset here and a k size subset here having the same color, because ith color, that is. So there is some Ax such that coloring of Ax is I, A minus x only, and there is some Ax such that coloring of Ax is I. But what is this plane doing? It is making sure that these two hemispheres are disjoint. So A minus x and Ax are disjoint, but they have the same color. The definition of the graph was two sets are related if and only if they are disjoint. These two are disjoint, so they are related but they have the same color. So this is a contradiction. I do not have that. So if I is equal to d plus 1, these are the only two cases because you have only d plus 1 sets. So what does it mean for I to be equal to d plus 1? Okay, so x in md plus 1, x comma minus x, both of them. X comma minus x is not in ai for any I. So if the hemisphere containing x contain any case size subset, then that case size subset does have a color. It is assigned some color. So x will fall in some ai. So this is telling you that the hemisphere containing x does not contain any case size subset.
But why is that?
Why? Okay, so did you get this argument? I'm going to erase this.
Yeah, first.
Okay, I'll just draw it again. So. Okay. This is a plane. This is x. This is minus x. So if I had some k size subset, of x, then by definition of coloring is that you assign it some color because it's the point of a vertex. So if it gets assigned color j, then x would belong to aj. But x is not in any ai is what I'm saying. So the hemisphere containing x contains no k size subset. The same is true of minus x. So the cardinality of hemisphere containing x intersection the base point capital X is less than or equal to, okay, plus minus x here, is less than or equal to k minus 1. Yeah, because it cannot contain a k size subset. So if I just take the union h of x union h of minus x, then intersect this with x, this cardinality is less than or equal to 2k minus 2. So these two hemispheres will contain at most these many points. Where are the rest of the points on this plane? How many rest of the points? N minus 2k minus 2, which is n minus 2k plus 2, which is equal to d plus 1. But this is a plane passing through the origin. The hypothesis was that no plane passing through the origin contains d plus 1 points. So this is a contradiction. So it suffices to show that I can somehow shift this so that I can get that all MIs are open or all MIs are closed. Well, I stated LU as in all AIs are closed, but the same thing holds for all AIs are open. For those who know topology, how do you go from an open cover to a closed cover when you have that it's compact? You use Lebesgue number lemma. Just fill it in with compact balls and take a finite union of all of them. Okay, so I'm going to show that you can get a subcover that is Ni Ni sitting in Mi so that they are open. Well, this part is done because they are open. It's only this one. I can erase the diagrams. I hope everyone understood this part. Okay. So suppose no point x satisfies x comma minus x in md plus 1. No. Okay. So this is md plus 1, or just for simplicity I'll call it m. This is minus m, and their disjoint is the thing. Since they are closed, there is some sort of minimum distance between them. That is, they can't approach each other as small as they want. Why is that true? Because it's compact. You can just find a subsequence. So, fine. So there is some fixed minimum distance. Call this delta. So now you consider this new set. Yeah, what I'm doing is you consider all points so that their distance to m is at most delta by 4. Like close enough so that it's not close enough to minus m. What happened is that this became sort of an open set. This is an open set, this is an open set, and their intersection, well, this is practically minus of this. So you got two open sets.
How can you make sure that if we include the points that it is open set,
Yeah.
still the distance is delta by 4? Like,
The distance is not delta by 4, but their intersection is trivial is all I'm saying. I can write that out. So what I'm doing is, I'm setting u equal to all points y in SD, such that the minimum distance between y and m is less than delta by 4. So claim is u intersection minus u is empty. And obviously, like since if you take any point inside m, distance from a point inside m and m is 0, so it satisfies this. And you have m subset of u. So I can, instead of taking md plus 1, I can take u and apply this argument. So it's the same. It's just that this needs to be covered, right? So, okay. If there exists z in u intersection minus u, then the distance from z comma u is less than delta by 4, or z comma m, sorry. But what does it mean for z to be in minus u? You're taking minus y, so that distance between minus y and m is less than delta by 4. I can take the minus and put it here. So you also get distance of z comma minus m is less than delta by 4. Point is, you have a z, you have m, this is delta by 4, and this is also delta by 4. So the minimum distance between m and minus m must surely be less than this. So that's delta by 2. But we assume that the minimum distance is delta.
yeah.
So it's a contradiction. Okay, so we got an open set containing m. So instead of taking md plus 1, I just take u. And I take m1 through md and u. The same argument holds. Done? So the chromatic number of kg n comma k is equal to n minus 2k plus 2. So I'm going to talk about one more problem and then we'll call it a day. So before that, again, I need a technical result. This is called the Ham sandwich theorem. So if I have A1 through An subsets of Rn, then there is a plane such that, so if you call the plane H, so what is a plane in Rn? A plane in Rn is just all points x1 to xn such that you have some linear combination ai xi is equal to some other number t. If this was 0, it's just a plane passing through the origin. If this is non-zero, I just shifted the plane up. So it makes sense to talk about H plus, where I copy everything and write greater than b, and H minus, again where I copy everything and write less than b. What does it mean in R2? I have a line. Everything above this is H plus, everything below this is H minus. So what is the statement of Ham sandwich theorem? Then there is a plane H such that H plus, the volume of H plus intersection AI is equal to volume of H minus intersection AI. What it means is that in R2, if I just give you any two spaces, any two sets, there is a line that cuts both of them in half simultaneously. So again, I will run out of time if I try proving this, but if you want, we can talk about the proof of this later. But again, this is a continuous version. This is a topological statement, I'm saying. And also it doesn't make sense to talk about volume for arbitrary sets. So the technical statement for those interested is instead of AIs, you take finite Borel measures. But that's fine. Okay, so discrete version. If AI So what I've done is, instead of taking volume, I'm taking the cardinality in both places. So how can I derive this from this is the question. The idea is pretty simple. You take each point, you enlarge all of them to become a small enough ball in that Euclidean space. Now they have a set volume. In RT it would just be 4 by 3 pi r cube, or if I got that formula wrong, something like that. So then you get proper volumes for each AI. Then you apply this, you get this plane that bisects all of them. But since you have taken small enough, none of these small enough balls will get cut arbitrarily by planes. They'll either get cut exactly in half or just miss it completely. So you can divide the volume of each of those ball points in half. So what happens is the points of these finite subsets either lie on the plane that's bisecting them or on either side. For the odd case, it must happen that the point lies on the plane, right? Because if I want to bisect, say there are k points here, 1 point here, k points here. 2k plus 1 points, if I need to bisect, then the plane must pass through one of them. Otherwise, there is no meaning to bisect. So that is a proof outline of the discrete version from the continuous case. Again, it is a little more technical than this, but I will run out of time again. Okay, I should make sense. Bisecting means cardinality of H plus minus intersection AI is this is the floor function. So there is a little cheek I can do where I just take, if I have even number of points, say 1, 2, 3, 4, this becomes a bisection. Because this point is included on the line, but on each side there are 2, at most 2. So there's 2 here, there's 1 here, so less than or equal to 2. So the definition of bisection still holds. But that's okay, we'll figure that out when we need to. I'm going to erase this again. So the problem we'll deal with is called the necklace problem. So what you're given is some open necklace with multiple very precious stones attached on it. So 1, 2, 3, I don't know. And you and your friends want to split this necklace in half, or not half. You want to split the necklace into multiple pieces so that beads, you can divide it into 2, and the beads on one of each type is equal to beads on the other of each type. In particular, we are assuming beads of each type come in even number, so that we can just split it. So the question is, what is the minimum number of cuts required? You are given that it's extremely hard to cut this wire and the beads don't just fly off. Okay. So the idea is put the necklace so there are D types of beads, and AI are the cardinality of AI is the number of beads of type I. That's just a notational issue. So put the necklace into the D. That doesn't make any sense, but fine. Along this curve. So this is basically a string. So I can, it's just a function from the closed interval 0, 1 to wherever I'm living. So I'm just taking t and assigning it, okay, this is the point you go to. The beads are placed only on integer values. Yeah. So AI are those gamma k such that gamma k is bead of type I. That's the definition of each of these AIs. And there are d many of them. Okay, fine. My bad, I don't need one here. Just notation. Okay. So now,
I didn't understand what does it mean, put the necklace in the RD and gamma t.
So basically this is a function from 0, 1 to r to the d, right?
Yeah.
So it's a sort of path. So I'm just asking you to align this necklace with respect to that path. And you can just shift, the beads are given to you nicely so that they're spaced by integer, not 0, 1, say 0, 2, how many beads? Yeah. N. So on each integer point you have a bead, and without that the string just passes through beads. So if I just take R2, then it's just an image of a segment. So it may look like this, may look like this. But since t coordinate is here, it's going to be injective, and so there's no cutting involved. So this is fine. So now you have d many subsets of Rd, and you have the discrete version of the ham sandwich theorem. So cut it. So you get a hyperplane.
Wait, what are the sets?
Here. So I want to. So you get hyperplane H dividing each di, each ai in this case, and the cardinalities of ai are even, that is given to you. Of pi there are evenly many. So what will happen is you will get the necklace exists, and you get this plane. So that everything above it, so for a given I, cardinality of ai intersection the upper part of the plane H is at most cardinality of ai by 2, and H plus minus, both are on the same side. Now it may happen that when I define this bisection, that a bead can lie on the plane. So how to take care of that? Well, just make the cut a little higher or a little lower. But the question is, why does this plane intersect? Oh, the claim was that you can always cut the necklace with at most d many cuts to do this division. So the question is, why does this plane cut the necklace in at most d many points? That is not necessarily true, but so the hyperplane is just given by, is there a definition? I'm not able. Okay. Y such that y1 through yd such that summation ai yi is equal to b. So suppose you have points of intersection. What does it mean to be points of intersection of the necklace and the hyperplane? The necklace is given by these coordinates. The hyperplane is given by this. So here it must be t, t square, t to the d. So what you get is H intersection necklace is just points such that summation ai t to the I, this is power, equal to b. The question is, how many such t are there? This is a d degree polynomial. How many solutions to a d degree polynomial can there be at most? D. So plane cuts necklace. And we know that bisection because of the discrete version of the ham sandwich, that is each ai is split in half. Okay, that is the end of my talk. Those are two problems in discrete one element solvent topology.